Good day guys, welcome back to Wiki Science YouTube channel. In this video, I'll put you guys through chemical equilibrium as well as being able to determine the equilibrium constant, also knowing the factors that affect chemical reactions at equilibrium. So guys, let's get started. What is chemical equilibrium? Chemical equilibrium is a dynamic equilibrium in which the reaction is said to be reversible and the rate of forward reaction is equal to the rate of backward reaction. The reversibility of this reaction is denoted with this symbol. So when it is not present in a chemical reaction, it shows that the reaction is not reversible. Looking carefully at the reactions given here, realize that from reactions 1 to 8, reaction 4 alone is said to be irreversible. So this reaction is not at equilibrium. Reaction 4 is not at equilibrium. How do we then determine the equilibrium constant? The equilibrium constant is dependent on the system which you are dealing with. For an aqueous system, we use Kc to represent the equilibrium constant. And in this case, we take it as the ratio of active mass of product to the active mass of the reactant. The product here is C. What we mean by active mass is the concentration of product to its power, and the power is represented as the mole. So this is mole of small letter c, and you also have that of D raised to power the mole, which is small letter d. Everything divided by that of the reactant. The components of reactant include A raised to power A and that of B raised to power B. So we can use this to express the equilibrium constant for system in aqueous form. Looking carefully at equation 1, you realize that it exists in aqueous form. So therefore, to get the equilibrium constant, we have it expressed as that of the product. So that is the concentration, which is CH3COO minus AN, the concentration to the power of its mole. But the mole here is an invisible one, so we will take it as invisible one, but we don't need to write this. So therefore, we are not writing this. The other component of product is hydrogen ion. So here, the number of mole is also 1, so it is invisible. We are not writing this. Everything divided by that of the component of reactant. What is the component of reactant? We have it to be ethanoic acid, which is CH3COOH. The number of mole here is also taken to be 1, so it is not written in as the power. We take the power to be invisible 1. Now, I want you to take note that when any of the components of reaction in aqueous system is said to be in solid state, that component will be having the molar concentration of 1. So looking carefully at equation 2, we have it to be the equilibrium constant is taken to be the active mass of product, which is the silver ion. The power here is also 1, so we are not writing this. And that of the chloride ion, the power here is also 1. We are not writing this. Everything divided by that of the reactant. Here we have it to be AgCl, which is silver chloride. But this silver chloride is existing in a solid state. So here the molar concentration here is taken to be 1. So we have the equilibrium constant to be expressed thus as the silver ion and that of the chloride ion. So here it is divided by 1. So there is no silver chloride being expressed here because the molar concentration has been taken to be 1. So this is how equilibrium constant is expressed for chemical reaction. The same thing is applied when chemical reaction is taking one of the components to be having water molecule in liquid state as the component of reaction. This water molecule will be having the molar concentration of 1. So therefore, considering equation 3, we have it that the equilibrium constant Kc is expressed as the molar concentration of product, which is CH3COOC2H5 divided by that of the reactant. The water molecule is not included here because the molar concentration of water molecule in liquid state is taken to be 1. This is not the same thing when water is existing as gas. Please take note. That is, you don't take water in gaseous state as 1. Here now we have it to be CH3, that of the reactant, COOH, and we have that of C2H5OH. This will be the expression for the equilibrium constant. Reaction 4 is not said to be at equilibrium because it is not reversible. For the 5th reaction, this reaction is occurring in a gaseous state. For reactions in gaseous state, we don't consider the molar concentration. Rather, we take note of the partial pressure of component of reaction. So here, instead of the concentration, we'll be considering the partial pressure. So let's express the equilibrium constant of reaction 5. The equilibrium constant for gaseous system is as well taken to be Kp instead of Kc. So here we have it to be the partial pressure of the product. The product here is NO2, but the number of mole is 2, so it will be to the power of 2 divided by the partial pressure of the reactant, which is N2O4 to the power of 8 mole, and the mole here is 1, so we are not writing anything here. So this is the equilibrium constant for a gaseous system. I will leave you with this number 6 to write the equilibrium constant. We move to number 7. The same factor that which is considered when you have one of the components of reaction in aqueous system to be in solid state is applicable for a gaseous system. When any of the component is occurring in solid state, you take the partial pressure to be 1. So here for equation 7, the equilibrium constant will be taken as the partial pressure of product, which is CO, having the power of its mole to be 2, over that of the reactant, which is taking the partial pressure of CO2, having the mole also to be 1. So it is invisible 1, and therefore we are not writing it. So this is the equilibrium constant of equation 7. I believe that by now we know how to express the equilibrium constant of gaseous system and also aqueous system. But there is an expression that relates the equilibrium constant of gaseous system with that of aqueous system, and is taken to be Kp is equal to Kc in bracket RT delta N. When you have this Kp to be equilibrium constant for gaseous system, equilibrium constant for aqueous system, R is the general gas constant, T is the temperature, and this delta N represents the difference between the summation of mole of product and the summation of mole of reactant. So here, when this delta N is equal to 0, it means that our equilibrium constant in a gaseous system will be equal to the equilibrium constant in aqueous system. For the 8th equation, you realize now that one of the components is water and is taken to be in a gaseous system. Earlier I said that you don't take water in gaseous system to be 1. Instead, you consider the partial pressure of water. So here, to express the equilibrium constant of the 8th equation, we take it to be Kp is equal to the partial pressure of product, which is water, to the power of its mole, which is 2, over the partial pressure of the component of reactant, which is hydrogen gas, and that of oxygen molecule. But looking at this equation carefully, you realize that it is not balanced until you add 2. So here to be having a power of 2. So this is how they came about the 2 that we're having here. Okay, now let's look at the factors that affect reactions at equilibrium. The first one we're going to consider is pressure. Pressure affects equilibrium in 2 major ways. It's either by increase or by decrease, as well as chemical reactions in a gaseous system. So if it is in a aqueous system, pressure will have no effect on the reaction. So for this first reaction, it means that since it's all in aqueous system, the pressure we have here will have no effect, and likewise for the second and third reaction. But for the fifth reaction, which will have to be N2O4 to give 2NO in gaseous state and gaseous state, here pressure will have effect on this system because it is in a gaseous state. An increase in pressure will favor the side with the lesser number of mole. The number of mole we have here is 1. The number of mole we have here is 2. So increase in pressure will favor this side at which we have lesser number of mole. Let's take this to be the back and let's take this to be the front. But since this is a reaction, we call it backward, and we'll call this one forward. So in this case now, since this is the side with lesser number of mole, we say that increase in pressure will favor the backward reaction. Increase in pressure will favor the backward reaction. If you are not considering decrease, decrease will be the opposite. Decrease will be the opposite. So if increase in pressure favors backward reaction, then it means that decrease in pressure will favor forward reaction. Let's take another example in which you have N2 gas plus H2 gas to give NH3 gas, which is ammonia. In this case now, you realize that the number of mole of reactant here is 4. 1 plus 3 will give us 4. And the number of mole of product here is 2. So in this case now, increase in pressure will favor the side with lesser number of mole, which is the forward. So here, increase in pressure will favor forward reaction, while decrease in pressure now will favor backward reaction, as it is taken as the opposite of it. That is about pressure. Another one we'll be talking about is concentration. Concentration affects chemical equilibrium in aqueous system. For instance now, equation 1, 2 and 3 can be affected by concentration. In this case, I want you to know that concentration affects aqueous system in 2 ways also. This is by either removal or addition. Now, whichever side in which the component is removed, that side is favored. Whichever side is removed, that side is favored. So now, when this component of reactant is removed, backward reaction is favored. But when any of the components of product is removed, it will favor the forward reaction. And when I remove any of the components of reactant, it will favor the backward reaction. Now for addition, addition will take opposite effect, in which the opposite side to which has been added is favored. Now when I add to the reactant, it means the forward will be favored. If I add to the reactant, the forward reaction will be favored. But if I should add to the product, the backward reaction will be favored. This is the case of concentration. Now let's come to the last aspect, which is temperature. Considering temperature, for instance, temperature only affects systems that are denoted with, and this enthalpy change can either be positive or negative. When it is positive, it's taken to be endothermic, and when it is negative, it's taken to be exothermic. So when a reaction is represented with endothermic, the forward reaction is favored. But in case whereby the reaction is given to be CO2 in gaseous state plus C in solid state to give CO in gaseous state, and is taken to be negative of delta H. In this case now, the backward reaction will be favored. The backward reaction will be favored since this is exothermic. Endothermic favors forward reaction, exothermic favors backward reaction. That is when it comes to increase in temperature. But when it comes to the case of decrease in temperature will take opposite effect of this. Decrease in temperature will take opposite effect of this. Decrease in temperature will shift the reaction to the back in endothermic, and it will shift the action to the front in exothermic. So let me just quickly give you a very simple method to denote the effect of increase or decrease in temperature. When there is increase in temperature, we take it to be positive, and when there is decrease in temperature, we take it to be negative. So what we now do is that we consider the reactants to be negative and the product to be positive, considering this your normal graph in which this place is positive of x and this place is negative of x. Now let's see how we quickly know which side is favored. When it is increase, which is plus times plus will give us plus. It means that forward reaction is favored. When it is decrease, which is minus times plus will give us minus, and that is backward reaction is favored. When it comes to the case of exothermic, plus times minus will give us minus, and we know that minus is for back, plus is for forward. So it means that backward reaction is favored. That is for increase in temperature. But for decrease in temperature, minus times minus is plus. So here the forward reaction will be favored. So this is how you simply denote how temperature affects chemical system at equilibrium. However, there are some certain cases in which they can bring up combination of two factors that affect system at equilibrium. For instance, looking carefully at this reaction is in aqueous system, meaning that it can be affected by concentration, and it is having, meaning that it can also be affected by temperature. But can it be affected by pressure? No, because pressure only affects gaseous system. Likewise, considering the second equation we have here, can this equation be affected by concentration? No, because this system is in gaseous system. Concentration only affects aqueous system. But can it be affected by pressure? Yes, since it's in gaseous system. And can it be affected by temperature? Yes, because enthalpy change. We've come to the end of this video, and I believe that this video has been so helpful in order to determine the effect of temperature change and the expression of equilibrium constant. Please keep sharing this video with your friend and ensure you subscribe if you haven't. Thank you for watching in detail. We'll see you next time.